Hi class, welcome to a review of chapter 22. This is chapter 22 on negative feedback. This is going to be part one. I'm only going to go up to section 22.4. We'll reserve the remaining sections for other parts. Okay, so what are we going to talk about? We're going to talk about negative feedback. And by that, I mean this kind of system which you've seen before. So we have some kind of process A that responds to an error. That error comes from a set point and a difference generated by a feedback like so. So that's plus minus. So Y0 is the output. K is the strength of the negative feedback. E is the error difference between the input and output. And then Yi is basically the set point or input if you're talking about an amplifier. Okay. All right. Remember, in an amplifier, the set point, as we normally call it, is actually becomes the input. And the idea of an amplifier is for Y0 to track, the input Yi. Okay. All right. So what I'm going to talk about then is the properties of this system. So what kinds of properties could we look at? Well, first of all, we could look at the transient response. So how fast does the system respond, say, to disturbances? Let's say I change the set point. How fast does it respond? Does it respond quickly, slower, depending on whether we have negative feedback or not? Second one is if we add negative feedback, does it affect the stability of the system? Is the system less stable, more stable if we add negative feedback? How accurate is it with and without feedback? So by accuracy, I mean how close is Y0 to Yi? Okay, so all right, how close is Y0 and Yi? Especially if the feedback is a unit feedback, all right, we expect Y0 to follow Yi exactly if it's very accurate. Number 4 is sensitivity. Is the system less or more sensitive with negative feedback? I mean, preferably we'd like the system to be less sensitive so that any manufacturing tolerances or genetic variation doesn't have that much of an effect on the performance of the system. So we want it less sensitive. And then finally, this is especially important for amplifiers. Okay, amplifiers. Amplifiers have to basically, amplifiers want to scale the input. So a perfect amplifier will just scale somehow the input. Okay, that's a perfect amplifier. Hopefully K is greater than 1 so that you get a bigger output, but the scaling is linear. And so that's what I mean by this linearization here. How good is our system at linearizing the input respect to the output? Does the negative feedback improve that or not? Okay, so these are the things we're going to look at. So the first thing we'll look at is proportional control, the transient response. I suppose I should add that these are all proportional control negative feedback systems, okay? So that A is proportional, the response of A is proportional to the error, okay? So transient response. Okay, so for this, let's look at a gene circuit, a simple gene circuit. So I have a gene that expresses protein X. Protein X degrades at a rate V2, and I'll assume that's just K2 times X. It's some simple mass action law. The rate of protein expression will be V1. There'll be an activator here that stimulates gene expression. And then the important thing is we're going to have a negative feedback coming all the way back from X to the promoter operator on the gene. Okay, so that's our system. All right, so what I'm going to do is let's write down, so the differential equation for this dx by dt is just v1 minus v2. Okay, and of course I know what v2 is. V2, because I've already said v2 is k2 times x. I haven't said what v1 is. In fact, I'm not going to guess what v1 might be, but what I will say is that it's a function of the activator and the negative feedback. Right, that's all I'm going to say. All right. Now, what I can do is at steady state, I'm going to linearize this system so that I get d delta x dx. And I'm going to form, I'm going to form, the thing that we're normally used to, this kind of thing. Okay, well, that's some kind of input. I'll call it delta p. All right, so I'm going to form that. So in order to form A and B, I need to differentiate. So, and I need to collect. These ones, of course, are the dv by dx's, and this one, of course, is the dv by dp. Okay, so let's collect all the dv by dx's first. So let me put a bracket. Let me put a bracket in here. So I have one dv1 dx, that's one x, and then the other x is on the second term. Note the minus. That'll be dv2 dx. Okay, and then I have delta x plus, and now the input is dv1. The input only affects v1, so it's the input is a for the activator delta a. So that's our linearized system. Okay. Around the steady state. I can solve this in the time domain. All right, we can enter this into something like Mathematica or whatever, get the time domain. And the time domain solution is given by this. I'll just write it out here first. dA delta I over alpha E alpha T minus 1. Okay, so that's the solution, right? So this is the full solution because it has perturbation to the state variable and a perturbation to the input, okay? Alpha is actually the term in brackets, so it's v1 dx minus dv2 dx. Now, oops, sorry. The other thing I want to ask is one of the things to ask is what's the sign for alpha? Right, what's the sign for alpha? Well, dv1 dx, which is this piece here, well, that's negative because x reduces v1, so this is negative. I got a negative there. dv2 dx, that's how x stimulates its own degradation. Well, that's positive, so that's positive. So that's the whole, that's negative. So the whole thing is negative, in fact, so it's less than 0, okay? And then just to be clear, the delta x0 is the initial condition. Okay. So what does this tell us then about the responsiveness? So you can see that alpha appears in the two exponentials. Okay. So they determine basically the decay rate. And the fact that this is negative means that these terms decay. This also tells us the system is stable. So these are decay terms. And in fact, the more negative alpha is, the faster it decays. And the more negative alpha is, the more negative this is. So more negative means that the exponentials decay faster. So you see immediately then that the transient response has improved, and it's due down to the negative feedback. This is this term here. So with negative feedback, the response of the system is faster. At least to small perturbations, it returns back to the steady state much faster than it otherwise would. So we conclude then that negative feedback can increase the responsiveness of the system. Okay, so that's one conclusion. There's another way of looking at this, that the responsiveness is through the frequency of response. Okay, for the frequency response. That's pretty straightforward to do. Give you a quick look at that. The way we'll do that is we have to compute, the transfer function, okay, which is given by si minus n dvx dx b, not b, N dV, and then the input was that. Okay, so N was 1, so it's one state variable. Number of reactions is 2, and the number of inputs was 1. Okay, so the dV by dx is a 2 by 1. That's dV1 dx, dV2 dx. That's all it is. Okay. But dV by dVA, I call it. That's also 2 by 1, but it's only got one non-zero element, which is the top. That one's there. That's because the activator doesn't affect V2. N, stoichiometry matrix, that was easy. That's just 1 minus 1. Okay, and I can put them all together, put them all into this equation, and I can derive H of S. Okay, so if I do that, I get this. S plus dV2 dx. And you see this bracketed thing turns up again. We saw it last time. Remember that was alpha. Okay, or the negative alpha, I guess. Okay, so now I can from this I can substitute in J omega and then find the amplitude of this. Okay, that will tell me something about the response, or how the amplitude varies with frequency. And if I do that, I get dV1 dA. That's basically that's basically the scaling factor. Whoops, and then square root of this thing here again, 2 dx minus dV1 dx squared plus omega squared. Okay. Now, there are various ways I can do this. The simple one is just to plot this as a function of frequency. So if I plot this, so the amplitude, okay, versus the frequency, these are both log axes, okay? If I plot this, I'll get a classic Bode plot. That's not a very good one. Classic Bode plot, something like that, okay? Where I have a bandwidth around here, okay? As I increase the negative feedback will actually push the bandwidth out into higher frequencies. There's a downside, though, which you'll notice here, that as I increase the strength of the negative feedback, of course, the denominator goes higher, so that the overall amplitude drops. So in fact, I get something like this. At higher frequencies, I'll get something like that. I can recover the gain by increasing this value here. And if I do that, I end up with, so this will be the without negative feedback, and then with negative feedback and restoring the gain, I get that, okay? So you can see that the bandwidth has gone up. So in other words, it can deal with higher frequencies, and it can do that because it's more responsive. Okay, so I already showed you that. The other thing is, of course, we get a reduced gain, which could be a bad thing. But as I said, I can try and restore that by increasing the numerator term. And I can do that in biology by just engineering more cooperativity into the binding of the activator to the operator promoter sites. But you can see from here that as I increase the strength of the feedback, the gain drops. Okay, so that's the other thing, we get a reduction in gain. So just to summarize, feedback increases the frequency response. Okay. But also it reduces the gain, unless we do something about it. And things like amplifiers, that's not so important, but because we start off with such an enormous gain anyway, in say in the op amp, which might be 200,000, even the loss of 100-fold loss in gain is not that bad. We'll still get what, a 20-fold amplification factor, even if we lose 100-fold of the gain. So it's not so bad. Okay, so that actually ends part one, in fact. All right, so part one, we've considered the transient response, the stability. We look at that next, and of course we look at the accuracy next, and the others. Okay, so I'll stop there.